Good morning. Once again, the final time this semester, continuing on with Professor Grenfell's lecture series on Math 12 Statistics for RCC, Riverside City College. All right, so here we are, Chapter 12. We're beginning, and we're only going to cover one section of this. We're simply going to be considering one-way analysis of variance. So ANOVA is the shortening of an analysis of variance. And let's just briefly discuss this idea. ANOVA is simply an extension of what we were doing in Chapter 9. So if we wanted to compare housing costs between two states, let's say California and Nevada, let's say we suspect that maybe housing costs are higher in California, but we could just simply test to see whether they're the same or not. So if we wanted to do this, in order to compare two populations' means, we would set up a hypothesis test as follows. We would say, okay, for the null hypothesis, H subscript 0, this is the status quo. We did not find any evidence of anything, so we cannot assume any difference between these two populations. That's what the null hypothesis is always saying. It's always an expression of status quo. We find nothing. We can't just make stuff up in terms of what we believe about it. We have to go with the evidence. And then the alternative hypothesis, this H subscript 1, just to simply compare these to just see if there is any difference and set aside what we think about which one is more, which one is less. We'll just simply use just a straightforward two-tailed test. We'd just say they're not equal. All right. So let us suppose, for instance, that we wanted to compare more than just two states. Let's say we wanted to examine, the differences between these four states: California, New Mexico, Nevada, and Arizona. I hope I got those abbreviations correct. And I forgive my geography, but I think they're near each other. So, it might make sense to compare these four states' average housing costs, right? So in order to do this, we would have to conduct, it turns out, 6 different hypothesis tests of the same format that we did in Chapter 9. Comparing these 4 different means, mu subscript 1 through 4, we would have to set up and perform hypothesis tests, comparing them in pairs, individually, one by one, going through all possible pairings of two states. And here, since there are 6 different possibilities, comparing mu1 and mu2, mu1 and mu3, mu1 and mu4, and so on and so forth, and then mu2 and mu3, mu2 with mu4, mu3 with mu4, and there are all 6 possible pairings. Just FYI that mathematics involved to determine the number of hypothesis tests that we would have to perform. That was determined in Chapter 4 techniques. Not necessarily going to be on the final, but you might want to just have that as kind of information. All right, so here we would have to do not just one single hypothesis test that compares 2 different means for 2 different populations, comparing 4 different populations, or in fact anything more than simply 2 populations together in one pair. That would involve not just double the amount of work, but probably at least triple the amount of work because of all of the possibilities for comparing two populations at a time, and thus the number of different hypothesis tests that we would have to perform. So that is our predicament. And you can kind of see why this might be something that we would really want to do. Obviously, if we can compare two things, we might want to compare a whole set of different things. And the techniques that we know thus far in order to compare populations, statistics, or parameters are kind of letting us down. They're limiting us. And so here, the idea of ANOVA, analysis of variance, is what we are going to consider to address this situation. Okay, so remember, ANOVA stands for analysis of variance. And since we are going to be looking at variance, we're going to be performing an F-test. So with this test, we're going to get two different estimates of the population variance and compare them. So they are the so-called between group variance and the within group variance. Yeah, it's kind of sort of hard to sneak that in there. All right, so we're going to now describe how we will be computing these two variances. We have to come up with their values first before we can compare them. And so we have to show what these variances are, or at least how we get them. So the first two values that we have to keep track of are denoted by capital N. That is the total number of subjects from all of the different samples that we've taken for all of these different populations. So, for example, if we take 100 people from California, 300 people from Arizona, 200 from New Mexico, and 400 from Nevada, I think I got those 4 different states and 4 different values, well, then we would have a capital N of 1,000. We would be adding up 100 plus 200 plus 300 plus 400, and that would be our capital N. So that's just an example. That is the total number, that's the total sum of all of the different sample sizes that we've taken. And then K, that's going to stand for the number of different populations that we are comparing. So in this previous example, comparing 4 different states, K would be 4. The next thing that we have to consider, and this is not new notation, we are going to, it is a computation that we have to do. We have to compute the sample mean and the sample variance for each one of the different populations that we are comparing. So we have chi bar subscript 1 and S1 squared. We have chi bar subscript 2 and S subscript 2 squared, and so on and so forth. So I just put dot, 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 and we'll go all the way up to, remember, there are K different populations that we are comparing. Thus, we have to have a sample from each one of these populations. And therefore, that last subscript, well, you know, in our example, K is 4. There's 4 different populations. So we would just have the sample mean and the sample variance for each one of these different values. If K is a different value, you'll have a different number of these pairs, but for each one of the samples, you're going to go ahead and compute its mean and its variance. The next computation that we have to do is compute what is called the grand mean. So this is the average for everything in the sample. We denote it, everything in the sum total of all of the different samples, the whole thing. We denote this by chi-bar, of course. The subscript on it is capital GM for grand mean. And the way that we compute this is we simply take the sum of all of the different data values that we have. So we denote that by summation of x. And we denote, and then what do we do? To take an average, to take a mean, we divide by the total number of values that we had summed up. So there it is. That is the grand mean. That's the mean of the entire data set for all of the populations, all combined together. Now, the next thing that we have to obtain are the two variances that we're going to be comparing for this f-test. So we have s squared with a subscript of b for the variance between groups, and we have an s squared with a subscript of w for the variance within groups. These were the two variances that we were going to be comparing, remember. Now, what we're going to be doing is we are going to be breaking this into steps, of course. And the book has, I would say, a fair amount of confusing notation that they don't explain very well. You know, it's easy to be a critic. But the notation that we're going to be running into, we're going to see a bunch of SS, and then a subscript, and then a bunch of MS with whatever corresponding subscript. It's either going to be a B or a W. Now, SS is going to be standing for sum of squares, and then to just kind of shorten it, MS is going to be the mean sum of squares, which is, so this mean sum of squares is essentially is also known as the variance, all right? So here they will kind of freely interchange MSB and S subscript B squared. And similarly for MSW, they'll just say that that is S subscript W squared. So it is quite a few steps, and they're a little bit complicated, so we got to pay close attention. Step one, you've got to find the mean and variance for each one of the samples. So remember, we're going to find a whole bunch of chi-bars, and then another fun computation, a whole bunch of S's or S squareds. Step two, we're going to compute big mean. Now, that's the grand mean, chi-bar subscript GM. The next thing after that we have to do is we have to compute the between group variance and the within group variance. And we're going to break that into two stages. So we're going to calculate sums of squares first, and then to find the variance, we'll do a division. So remember, SS stands for sum of squares. We're going to calculate the sum of squares between groups and the sum of squares within groups. So just before we move on to anything else, let me just remind you, to compute the sum of squares between groups, we use this formula. It's n subscript I times chi-bar I minus chi-bar subscript GM, and that whole quantity squared. And we add up all of those values for each one of the samples that we've taken. And then the way to calculate our sum of squares within groups is we do the sample size minus 1 times the variance for each one of those groups. And then we add up all of those values. So yeah, we're breaking this down into stages. Stage 4, we're going to go ahead and find our mean squares. So first we just added up a bunch of things. Then we're going to divide essentially by the degrees of freedom to find the mean sum of squares for between groups and the mean sum of squares for within groups. And here are the formulas for those. And so to calculate the mean sum of squares between groups, MSB, we'll just simply take SSB and divide by its degrees of freedom. So the degrees of freedom for the numerator are k minus 1. And that is, well, like we've mentioned, that is the variance for between groups. So you can either denote it by MSB, or you can say it's S squared with the subscript of B on it. So MSW is just SSW divided by its degrees of freedom. And in the book, there's a fancier formula. It looks kind of more complicated, but we can simplify that whole expression into just N minus K. And so this is going to be our S squared with the subscript of W for the variance within groups. And remember the degrees of freedom. This is always going to be in the denominator. So these are the degrees of freedom for the denominator. They are N minus K degrees of freedom. So that is what we'll do there. Remember, to compute a variance, we're always just going to be taking a sum of squares and then dividing by the degrees of freedom to give us the average, the mean sum of squares. And then the last step, so that we can move forward with the hypothesis test, is we'll compute the F statistic. We'll compute the test value. So the F value for the F test is going to be MSB divided by MSW. So it's just kind of easier to write it like that. But remember, this is an F test, and so what do we do for an F test? We take one variance divided by the other variance. The degrees of freedom that we will be using to look up the critical F values for our hypothesis test are going to be these. Degrees of freedom for the numerator is k minus 1. Degrees of freedom for the denominator are n minus k. So once we have done all of that, remember, this is just to do one step of the hypothesis test. If we're using the traditional method, we compute the test value in step 3. It's just one out of the 5 steps. If we're using the p-value method, we do it first. We do it in step 2. But notice that in order to get that F value, we have to do a whole lot of stuff. And so what we will usually do is we'll organize our computations, our work, our numerical values, into a summary table, or sometimes it's called a source table. So they're usually organized like this. They have the source on the first column. So we have the first row of this is the between group information. Then the next row is within group. And then at the bottom here, we have total. Now, not all of these squares in this table are going to be filled in. But what we'll do here is we'll say, okay, between groups, the degrees of freedom are k minus 1. So we'll figure out what that is for our particular problem. We have n minus k for this. And when we add these up, we should have that be equal to the total. So that would simply become n minus 1, right? The sum of squares, so we will compute these and list whatever these are here. And the nice thing about this is, like we saw here in the first column, if we take this value plus this value, it should be equal to the total value, right? And again, it's not necessary really to fill in all of these values. All we really care about is what is the F value. Now, in order to get the mean, we'll just be doing this. We'll take the sum of squares, this one, divided by the degrees of freedom, right? And we'll write that down right here in this square. And we'll do the same thing here, but then for the rest of the table, we're not going to be filling it in because Here, it doesn't make sense to do anything for that. These will not have any values in them. The last little thing, remember to compute F, you divide MSB by MSW, so we'll just be taking this value, dividing by this value, and write that in for our F statistic. So that is summary table for an ANOVA test, also known as a source table sometimes. I think they call it source table. And we're going to stop here and go back into a separate example. We'll go through doing all of this, and then maybe just a few fast ones where they've already done the source table or the summary table for us. All right, so we'll stop this one. This will be just the introduction to Chapter 12, Section 1. And that is all for this video. Thank you.